Okay. Hello everyone, and welcome to the UVA Gravity Seminar. Speaker this week is Dr. coming to us from Princeton University, the Princeton Gravity Initiative. He got his PhD just in 2022 from the University of Chicago, working with Bob Wall. With that, get started.
Okay, so thanks for the invitation. Thanks for the introduction. So what I want to talk to you today is about this fairly long title of infrared finite scattering theory in quantum field theory and quantum gravity. This is a fairly old problem, as I'll explain. I think it goes back about a century of having what I guess I will explain to you is a well-defined scattering theory in these theories, okay, of quantum field theory and quantum gravity. And you'll see basically all of the essential problems just from the classical structure of the theory alone. So most of this talk, I'll just basically be explaining the classical structure, and then we'll see exactly what happens in the quantum theory and why all of these nice classical structures that maybe some of you might be familiar with become a significant problem when you want to do quantum theory. Okay, so this is all, well, this is a long title. This is a very, long paper that kind of encapsulates, well, all of my thoughts about this problem. But my goal today is to kind of give you the kind of basic punchlines. And I think the basic punchlines are very clear and easy to understand. And then you'll see why we had to go through all the machinery we had to build to basically solve this problem. Okay, so this is work did with Bob Wald and Cardiff Prabhu, and there's some work maybe I'll explain at the very end, which is some follow-up that should appear shortly. Let me see how to advance. So let me just start. It's not, let's just start very slow and just think about what is scattering theory and what we're trying to do. Well, conventional scattering theory, if you open up Paskin and Schroeder and other textbooks with massive particles, is perfectly well defined. This has been known for many years now. But one runs into these significant issues in defining scattering theory with massless particles. So this has been also very long known. The issues that I'm referring to are these infrared divergences that one encounters when doing this problem, which I'll explain. And this really comes when, if the massless particles are coupled to massive particles or undergo suitable self-interactions like in gravity, you're always going to have this issue of these IR divergences. And later in this talk, I'll explain how these divergences are related to an observable known as the memory effect. So I'll explain that link between these two. Well, I mean, quantum field theory books don't just stop at massive field theory, they do massless field theory. And it was pointed out, well, really as early as the 30s, and later refined by Weinberg in the 60s, that we can compute some things even with massless fields, even though the S-matrix is absolutely undefined when you include massless fields. One can consider these so-called inclusive cross-sections. There are certain observables I can write down that turn out to be insensitive to low-frequency physics. But again, the S-matrix is undefined, in determining which observables are the nice observables that are going to be insensitive to the low-frequency physics is more of an art than a science. I'll explain more of that later in the talk. But in any case, the standard scattering theory cannot keep track of all degrees of freedom. If all of the recent questions about holography and asymptotically flat spacetimes, this soft hair stuff that has come out recently since 2016, any entanglement between high frequency modes and low frequency modes, none of that can be addressed within the standard framework because you can't keep track of those degrees of freedom. And really the question at the end of the day is, does there really exist an S-matrix that just keeps track of all data? Right? That's the question that I'll be trying to address. And you could, quantum field theory books don't even usually include this part, but remarkably, if you go, into the literature, Faddeev and Kulish in the 70s actually came up with a proposal that gives a well-defined S-matrix, no IR divergences, no issues at all in QED with massive electrons. And what I'll explain later in this talk is in what sense is the Faddeev-Kulish construction a preferred construction in some sense, and how it can it be adapted to any other theory? And really just the question that I want to leave or end this slide on is just, is there a well-defined S-matrix? Okay, in more general theories, quantum field theories and in particular, I'm interested in quantum gravity. Okay, so that's the question, is there a well-defined S-matrix? And we will just answer this question hopefully by the end of this talk. Okay, are there any questions so far? I haven't defined most of these words yet, but every word will get a definition by the end of the talk. Okay, so the first word I need to explain is the memory effect. Fortunately, there's an imprint of the previous slide on the, okay, so this is so that you can remember what I said before again. Okay, so the first thing I need to explain is the memory effect. This is the classical gravitational wave memory effect, which is that if I have some ring of test masses here, and I allow a burst of gravitational radiation to pass by this screen, these test masses will, relatively oscillate in the characteristic fashion that hopefully some of you have already seen and was detected. And later, if you wait a while, if you go to, low frequencies lower than the interaction timescale of the event, these test masses will become permanently displaced relative to their original positions. And this is the gravitational memory. This is, a very innocuous effect. You just wait a while and your detector is permanently displaced. You can, calculate this effect. It's not so, difficult. Initial displacements of your masses, and this delta here tells you what the final relative displacements of your masses at leading order in the distance the source of the burst of the radiation. Okay, so this delta here is what's called the gravitational memory tensor. If it's non-zero, that means that I have a non-trivial permanent displacement of my detector from early to late. Okay, so there's a gravitational effect. There's also an electromagnetic effect. I don't need a whole array of test masses. I just need a single charged particle. And if I have a burst of electromagnetic radiation passing by my charged particle, then if it receives a net momentum kick due to the burst of the radiation, and this is a momentum kick measured at leading order in the distance from the source of the radiation that I'm considering, then that's an instance of the electromagnetic memory. Okay, so these are just how I would detect these effects. And one thing you might ask is, well, first of all, what kinds of sources of radiation am I thinking about? Well, I'm really thinking about radiation coming from scattering sources. So this here could be the scattering of some charged particles in electromagnetism, or the merger of some black holes or stars in gravity. But the key thing, or the picture that I really want, is that the radiation, is negligible at early and late times in retarded time near null infinity, but it is potentially fairly significant in the intermediate. Okay, and if we consider radiation sources like that, we can immediately write down what memory looks like in terms of these waveforms and that I get at null infinity. So U is retarded time moving up and down null infinity. This cone angles, these cross sections of null infinity are these angles here, and so therefore a field is basically a tensor that's a function of U and angles. Okay, that's the radiation field. And if I look at the electric field at null infinity, well, I said it was the permanent momentum kick due to a passage of burst of radiation. So therefore, by the Lorentz force, it's the integral of the electric field. If I get a total integral of the electric field as non-zero, that means I have a net momentum kick. And therefore, the memory is given by this integral of the electric field. If you write it in terms of the vector potential at null infinity, well, the electric field is just the derivative of the vector potential. And as a result, any waveform that has memory at scribe, so any waveform that I can, that I might be able to detect at scribe, if it has memory, then it will, undergo these oscillations due to whatever's happening in the bulk. But if it has memory, it gets a permanent offset between early and late times. That's just putting this time derivative of the vector potential into this thing. That means that the memory is a change in the vector potential between early and late times. Okay, so that's all that looks like. in the gravitational case is nearly identical. I mean, these pictures, I really did just copy and paste, so they should really look identical to you. And the memory is now the integral of the news tensor, that's the gravitational radiation degrees of freedom. The news is the time derivative of the metric at scribe. There is a non-trivial memory effect. That means that the metric gets a permanent offset between early and late. So this is the kind of signal I'm looking for if I'm getting a radiation with memory. Okay. And so this is all purely classical, and let's continue to the classical slide. It's really useful, and it will be very almost essential in the quantum theory to recast the memory effect in terms of charges and fluxes. So this is very important. I'm going to spend probably the full 5 minutes just talking about this so that you fully understand what's happening in the quantum theory. So in the electromagnetic case, I want to think about these charges here, which are, you take on a cut of null infinity, which I told you was a sphere. I integrate the radial component of the electric field against a function of angles on that sphere. If lambda was a constant, that's the integral of the radial component of the electric field, which is the total charge on that cut. But now I'm going to let lambda be an arbitrary function of angles. And why would I do that? Well, you can write a very useful formula for the memory in terms of these charges. So what do? You take this cut, you take it all the way to u goes to infinity, all the way to what's called time-like infinity. That's what this charge I plus means. If I take the cut all the way down to u goes to minus infinity, that takes me all the way down to what's called spatial infinity. That's what that charge is. If I take the difference of those two charges, I'm just computing some two numbers and taking their difference. And I also integrate the total flux of any massless charge current that I might also be accumulating out at scribe. So that's what I integrate here, the total flux of any charge current against that same lambda. That's a formula for the memory effect. Okay, so there's an equivalent way of describing the memory effect in terms of a difference of charges living here and here, as well as any fluxes of current that go out. Okay, so I gave you a new formula for the memory effect as opposed to the one before. They're equivalent. Okay, so why am I interested in that? Well, you can also do that for any incoming data. If I have any incoming radiation with memory, I can write that in terms of the difference of charges at time like infinity. They're just these integrals of these, radial components of electric field evaluated at different places. I take those differences. If I have any incoming massless charge current, I also add that in, and then I can compute the incoming memory. Okay, so these are just formulas that I can use to write these down. And the reason why that's very interesting and very useful, going to be very useful in scattering theory, is because these charges match. If I'm taking this charge all the way to spatial infinity from the past, and this charge all the way to spatial infinity from the future, they match onto each other. If lambda was a constant, this would be conservation of electric charge. But now this is true for every lambda. And the matching condition, it's not so important that you remember the exact matching condition. It's a antipodal map on the sphere. So the in lambda is related to the lambda from the future by an antipodal map on the sphere. That's not so important. All you have to remember is that there is a matching between incoming charges to outgoing charges. So this is a very strong constraint on scattering. Any incoming radiation with memory will generate charges in this fashion, which have to match onto any outgoing radiation. And this is going to be very useful for the whole discussion. Okay, is there any questions about these charges? Yes, go ahead.
These charges are these defined by Hilbert or they are not?
Not in the strict sense, because these gauge transformations really only exist on the boundary. You can do an arbitrary gauge transformation in the bulk and add onto it, add onto these gauge transformations, and you're basically allowing all gauge transformations that tend to lambda as a function of angles on the boundary. Like for example, if you just want to do total electric charge, you could do a constant gauge transformation everywhere, right, in the space of time. This one is kind of, it's really arbitrary what you do in the bulk. These charges are really only defined as boundary charges at infinity. So there's no like integral of some charge, local charge current in the bulk that you then match onto a boundary integral. These charges are just defined independently of that. And the reason why they're useful is exactly the relations I'm using now. There's no really useful bulk notion of these things. Okay, that's a great question. Okay, so we're all happy with these charges. I've made them up largely, but they satisfy some nice rules. Very nicely to memory, which is, I haven't told you why that's interesting, but hopefully, on its own, it's quite nice. Okay, very good. So again, there's almost an analogous, nearly analogous story in the gravitational case. These charges now, they're not integrals of they're integrals of the analog of field strength curvature. It's again not important that you remember that. If F was a constant on this cut, that would be just the total mass on this cut. Now I'm going to let F be an arbitrary function of angles. So I'm now keeping track of, you can think of like different multipole moments of mass. That's what these charges are. I'm taking the difference of these charges from the future and the past. That computes the out memory up to a total flux of now it's gravitational radiation energy. The nu squared tells you what the gravitational radiation is, like the electric field squared tells you the electromagnetic radiation. And that's what's contributing into this formula now, where the total flux of energy going out to Scri. You can also write a similar equation for the incoming data, and these charges match in exactly the same way as before. I'm hopefully not giving the impression it's trivial to prove any of this. It's its own body of work to prove it, but now we can use it to understand relations about the quantum theory. Okay. Yeah.
So depending on what F you choose, you get different forms of power.
Yeah.
So with gravitational wave version, there's one memory equation.
Yes.
So how do we pick our unique F so that
No, sorry. Yeah. So so this is true. This relation is true for every F, for any F, for a large class, right? For a sufficiently large class. So if I tell you delta smeared with every F, I'm telling you the delta has a full function of angles. So it tells you the full memory everywhere. If you were, so does that answer your question?
so yeah. That means memory is really the delta. Memory
is really the delta. There's a nice way of writing it in terms of charges if I smear it, but this F is really just this, this F is arbitrary. I'm allowing you to define all of these charges for all possible F's. So basically, there's another way of writing this formula where you get rid of the F. It's just it's not going to be, it's nicer in the quantum theory to put the F in. That's why I just left it there now. But yeah, I mean, you can, there's a putting this delta and then just integrating out all the F's, right? And then you just have a relation that's true at every angle. Okay. Good question. Okay. Okay, so this is the story. There are these charges that exist that keep track of the memory in this very precise way. And so why is that why is that useful? Well, in order to explain why that's useful for the problem I was setting up before, is to we really should first understand what is the quantum degrees of freedom now, as opposed to the classical degrees of freedom that live off at non-infinity. Okay, so this was already done way back in the 80s, and Ashtekar really nicely showed is that the radiative degrees of freedom of quantum gravity and electromagnetic fields can be quantized at null infinity. So I can talk about the quantum radiation degrees of freedom on this boundary. I'll explain exactly how. And Ashtekar, well, he nicely pointed out that this is also in the absence of any bulk theory. Like he's, the quantization of gravity on the boundary is like kind of a kinematic statement. It's basically stating what are the space of gravitons that live on the boundary. It's not a dynamical statement. So you can define everything that I'll be talking about today just at the level of kinematics, basically, which is, so everything I'll be talking about today is true in any theory of quantum gravity. Let me just say that. And how do you do this? Well, let's just do the gravitational case. We can also do the electromagnetic later. Well, the standard Fock space. So if you remember quantum field theory, you build a Fock space, you start with a one particle Hilbert space of gravitons. A Hilbert space is basically a space in which I define an inner product, or a norm in this particular case is what I'm giving you. And the particular details of this norm are not so important. All you have to remember is that it depends on the Fourier transform of the particular metric I want to quantize. And it also has this funny factor of omega sitting here as well. Okay, and it's an integral over frequencies over that Fourier transform and an integral over angles. So all states in the standard Fock space used in Pascal and Schroeder and otherwise have to have finite norms. So you can imagine, think of all the space of waveforms you can write down, plug them into this norm. If they're finite, it's an admissible state in quantum gravity at the moment. Okay, from this point of view. Okay, we can already see the problem, which is that now let's just try plugging in a state with memory. Well, if the state has memory, that means that as I told you, the change in the metric between early and late times is not zero. That means that the Fourier transform must diverge like the Fourier transform of a step function, basically, at low frequency. Must diverge like 1 over omega. And as a result, if you plug it into that norm, you're going to get that the norm of any solution with memory is logarithmically at low frequency. Okay? So that's this is a very key point. Every solution with memory that I could possibly write down has infinite norm quantization. So if you do the standard quantization of Pascal and Schroeder and just pull it back to null infinity, this is what you're getting. Okay, to put a finer point on it, the standard Fock space of states used in scattering theory does not contain any states with memory. Okay. And any state with memory will have infinite norm in the usual Fock space. I probably don't need to convince most of this crowd, and as I basically explained to you for the earlier part of this talk, there is absolutely nothing physically wrong with states with memory. They unavoidably will occur in scattering theory. LIGO will detect the memory effect. However, infrared divergences arise when you try to pretend that they're supposed to belong in the standard Fock space. So what is scattering theory doing? It's producing states with memory, and then we're acting as though they live in the standard Fock space, and we get an infrared divergence when we assume this. I'll explain a little bit more, but if there's any questions at this point. Okay. So
curiosity, what is that way again, the norm actually? Why do you need the separable midges?
it's called the Klein-Gordon norm, and so the Klein-Gordon norm has one derivative with respect to time in it. So it's like roughly it goes like the Fourier transform phi. If it's just a scalar field on a spatial slice, the integral is like something like phi time derivative phi. So and that sounds imaginary, but the Klein-Gordon norm is defined with minus I, and that makes it a real thing. Yeah.
Similarly, I guess might be a silly question, but could you just define a different norm?
Yeah, but we're going to do that in a second.
Okay.
But a different norm is going to give you a whole hill of states. And so now we got to keep track of what are all the states relevant for scattering theory, which is the next. I think it's a slide after this one. So answer your question in 2 slides. Okay, so obviously, as I alluded to before, this is not a new problem. People have been dealing with this for about a century. And generically, the outstate, again, will just have memory. The standard out Fock space contains only states with no memory. You can do this in electromagnetism just as much as in gravity. You get the same result. If you try to put an outstate with non-vanishing memory and try to stick it in the standard Fock space, you will get an infrared divergent expression for the state. And it's just not going to be defined. Fock space. What is the standard approach? Well, the standard approach is to put in an IR cutoff on the state. So then you can pretend that the state lives in the standard Fock space. And then you can compute what's so-called inclusive cross sections by summing over all possible low frequency gravitons or basically what you're doing is you're trying to find some observables which are insensitive to the low frequency physics. Obviously, well, that's perfectly good for the LHC and was very nicely, done, explained by Bloch and Nordsick and refined later in the 60s. And it really does work for calculating, some cross sections of observables that you really know don't depend on the any low frequency physics. But let me just explain the viewpoint of most of the past 20 years. I mean, it's really unsatisfactory first from a fundamental point of view. S-matrix as defining what we mean by quantum gravity, that's clearly not admissible. It also, one can't discuss any issues that have been of particular recent relevance, such as entanglement of low frequency observables with high frequency observables, the information content of anything of low frequency. If you want to have the S-matrix actually be unitary as a map on a Hilbert space, it's not a map on a Hilbert space. If you want to do anything related to flat space holography, you really want to keep track of low frequency observables, and I could go on and on. It's, the real question is basically, does there really keep track of these all degrees of freedom, not just the ones possibly relevant for a collider experiment that you might be interested in. And unfortunately, that's getting cut off. But and the word divergence gets thrown around a lot in quantum field theory. So let me just take this one, minute or a few seconds just to explain. So UV divergences do appear in quantum field theory. Those are fundamental in defining products of operators, and there's a whole sophisticated renormalization theory in kind of dealing with those. IR divergences are not of this character. IR divergences simply arise from forcing a state into a Hilbert space representation. It just doesn't belong. Okay. And so the question that Alex is raising, which is a very good question, is, well, where do these states with memory actually live? They don't live in the standard Fock space. And again, they're perfectly legitimate states, and a Hilbert space of states with memory can be easily constructed. If we take all of our states with no, I gave you a whole class of states with no memory, and what I'm going to do is perform it, what I called it a field redefinition. That's way too fancy, but I'm doing a very trivial thing. I'm just taking the gravitational radiation degrees of freedom and as an operator, and I'm just going to shift it by any classical solution. But now I'm going to give that classical solution memory. Okay. So this is just a map. This is just a thing I can do the operator. That it doesn't change the algebra of observables. It doesn't do anything. It just shifts my operator by a classical solution now with memory. I'm just giving the operator memory, even though it didn't have it before. Okay. And now what happens to all the correlation functions? If, the 1-point function of the news in the vacuum was 0, now the 1-point function of the news of this new state that I'm defining is going to be expected value, which it has memory. Okay. And the 2-point function will shift, all the n-point functions will shift, and I'll define a whole new class of states. None of these states live in the standard Fock space because they all have memory. In particular, every state is going to be a state of definite memory with the eigenvalue of the memory operator just being delta. Okay, so what I'm doing is I'm giving you a whole Fock space of states of definite memory, delta. And all of these are unitarily, this Fock space of F delta is unitarily inequivalent to the standard Fock space. Okay, so because all of these states have memory. Each of these F deltas for different delta are unitarily inequivalent to each other, because F delta, the Fock space of delta 1 has all states of definite memory delta 1. The Fock space of delta 2 has all states of definite memory delta 2, and so on and so forth. So they're all going to be equivalent to each other too. Okay, so I made the problem. So I said I'm trying to fix a problem, and I've made it, uncountably worse. Right? So there are an uncountably infinite number of these in and out Fock spaces, F delta, and labeled by all possible in and out memories that I can have. And the memory is not conserved. If I send in a state with no memory, I will scatter out the states with memory. Memory is produced in scattering. So it's not conserved, and the standard S-matrix just doesn't exist, right? As a map between zero memory to zero memory. I'm going to produce memory in my out state. So if we want to go beyond inclusive cross sections and have a well-defined S-matrix, you need to include states with memory in the Hilbert space, from the in states and the out states, as in one construction.
Sorry, so did you introduce the IR cutoff?
Mhm.
You didn't, but you
No.
said you serve the Fock space and then you said.
Yeah, exactly. And so if I don't put an IR cutoff, I'm kicked out of the Fock space if I try, but I can still write a new space of states. That's what I'm saying. And all of those states will have a different memory. And you get a new space of states, one for every possible memory, basically. And this happens sometimes. If anyone's familiar with super selection sectors or something in quantum field theory, you get a space of states labeled by some super selection sectors. The nice sectors is that they're labeled by a conserved quantity. So I can pick one and I can always stick there. And I don't have to ever consider the uncountably many other possible sectors. For example, total electric charge is a super selection sector, but charge is conserved. So I can just pick one. The memory is not conserved. So now the scattering is totally uncontrolled. Yeah.
So this is probably just on me because I don't remember a lot about quantum mechanics.
Yeah.
But, so in order to have an standard sense, you need to be mapping between two spaces that are the same in this unitary.
Yes. Yeah, you have to be.
So you can't just have, a matrix that starts in one.
I mean, you can, but the question is guessing what the Hilbert space is.
Okay.
Right. So I'm not going, my out state will not live in all of these uncountably many Fock. It'll select out some countable selection of them. And the question is, which countable selection do you scatter out to? So you're again preempting my next slide. So this is good. But yeah, the question really, well, let me just go on and then you tell me if I don't answer your question. Okay, so the question is basically what sort of Hilberts, as Alex was saying, what kinds of Hilberts could we choose? We need to include, if we want to have a well-defined scattering theory, we need to include a sufficiently large or sufficiently many of these F deltas together and ensure this, that the Hilbert space scatters into itself. Okay, but again, the problem is that the memory is not conserved. And so any construction that just stitches these Fock spaces together will not generically be preserved under scattering. So let me give you some examples. So one could consider just take the direct sum over all possible memories. I allow the zero memory Fock space, the memory one Fock space, and memory two, and I just direct sum over all of them. This is an uncountable direct sum. So it's really not very useful for scattering theory. For example, if you wanted to, you can't choose a basis on this space. It's uncountably large. So, if you wanted to compute amplitudes or anything like that, that's not really very well going to be possible in this particular approach. And more to the point, it's absolutely, it's provably not possible that if you start with an element of the direct sum, you scatter into a Fock space. That's an element of this direct sum. I can explain that in more detail, but for example, consider the zero memory Fock space. That's an element of this direct sum. It doesn't scatter into this space. One could try a more refined approach, which we also considered, which is called a direct integral. You integrate over this space of memories. The devil is basically in the choice of this measure. So normally when we integrate over nice Hilbert spaces, like when you do momentum decomposition or things like that, we're integrating over a finite dimensional space. The space of memories is an infinite dimensional space, which means the choice of measure is absolutely not something that is a priori given to you. And you can, we investigated this problem. It would be its own talk just to explain this, but basically we ruled out this construction also. But the key thing is that if you just going back to this bullet point, if you just arbitrarily stitch these Fock spaces together, it's not clear at all, or in many examples you can explicitly show, there's really no way to ensure that the out Hilbert space will scatter into anything that looks like what you chose for your in Hilbert space. because you're not choosing it based off any symmetry principle. You're just making up some measure or some other ad hoc construction and assuming that your out-Hilbert space will also live there. Okay, so the question really is, does there exist an in-Hilbert space of states that scatters to a pre-chosen out-Hilbert space? That's how we do scattering theory at the moment, right? We pre-choose an out-Hilbert space, and I tell you an amplitude you go between one element of the in to an element of the out. Okay? So like any old problem that's been around for a long time, two Russians solved it and in the 70s. And this is not how they explained it. This is not even anywhere close to how they were thinking about it, but this is exactly what they did. The key idea is that the charge at spatial infinity is a conserved quantity. So if I start with in Hilbert space, which is eigenstates of this charge now, which are conserved, it will then map to an out Hilbert space that is also an eigenstate of this charge because of this matching condition that I told you about before. Okay, so somehow they were able to see this from their, but with in this language at all. And the reason why why it was very difficult to see if, well, the rest of this talk, which is how this could work in any other theory, is because you really need to reformulate it in this kind of manner to then see if it's going to work in any other theory. But so let's explain how this works in massive QEDs, QED with massive electrons. So what are these eigenstates? What am I doing? Well, I'm taking this charge at past time like infinity, and I'm I'm correlating this charge, which is determined by the incoming electrons, and I'm correlating it with incoming memory. So let me just show you a picture, which is unfortunately a little cut off. But if I take in an in state of the electron, let's say like a plane wave state of the electron, which is coming in, which is massive, so it's coming in from past time like infinity, that has a definite charge at past time like infinity. You can think of this as like the kind of angular distribution of the electric field. That's what I'm getting here. Okay. Now I'm going to fix the charge at spatial infinity to be a definite function, whatever function you decide. Okay. And I'm going to then use my formula to solve for exactly what memory I need with this incoming state. Okay. So what am I doing is I'm sending in this electron, I'm tensoring it in with any state. It can have any behavior at any high frequency you want. At zero frequency, it's pinned by the incoming momentum of the electron and the charge at spatial infinity. Okay, so this is any state that you're allowed to put in here with this property, which I can uniquely solve for. Okay. And then I can integrate that up with some nice wave packet and get a very nice state to send in. It's a little funny, who ordered that? Like I send in an electron and it has to know about, you have to send in a bunch of coherent radiation from infinity along with this electron. This is what people call dressed electrons, by the way, or soft dressing. This is precisely it, where the incoming radiation has to know a lot about, well, exactly the incoming momentum of the electron in this precise manner. Okay. But you can do it. So this gives you a full Hilbert space. I did this for one electron. I can do this for any number of electrons, and this gives you a Hilbert space of what's called dressed electrons. I've wondered that for quite a while. What these are. This is exactly the construction, and there's one. Well, this is exactly what Faddeev and Kulish did. There was one issue with this construction, which was pointed out only like 9 years later, which is that these charges, so I get a Hilbert space of definite charge, but these charges are not Lorentz invariant. So under a Lorentz boost, so imagine if I take the spherically symmetric part of this equation, that just tells you that the electric charge under the Lorentz boost is unchanged. This function becomes that's dividing this angular function becomes just one in that case. But in general, for this full function of angles, the radial component of the electric field changes under a boost. Okay, and so as a result, these charges all change under a boost, and therefore these charges are not Lorentz invariant unless I set the total charge, all of these charges, all higher harmonics of these charges, to 0. That's the only one that's going to be Lorentz invariant. And in particular, unless if I don't do that, Lorentz boosts cannot act on this Hilbert space unless I set all of these charges to 0. Okay. It's like, for example, if I'm picking a Hilbert space of definite position in quantum mechanics, momentum cannot act on that. And I don't have any space where I can do that. In this particular case, there's one example where, where I can act with Lorentz boost, and that's the only case in which I map the Hilbert space into itself under a Lorentz boost, and that's the only case. The only case that happens is when I set all the charges to 0. Okay. So that's kind of funny. So what am I supposed to do? So the angular, well, in particular, the angular momentum is undefined for all incoming states of the Faddeev-Kulish construction, unless you set all of the charges to 0, including the electric charge too. Which means that in order for this to work, what was stated in this paper, well, if I'm scattering 2 electrons, who's to say there aren't, and I dress them in whatever way you want me to dress them, who's to say there aren't 2 positrons also dressed that are sitting behind the moon somewhere, when I'm doing my scattering. And that's the justification. I'm not, hey, don't shoot the messenger. I'm just explaining what they did. This is the justification for doing so. And they said, okay, well, for all physically reasonable things, why not just stick to total 0 charge sector? We dress everything in exactly as we were going to dress them before. And, that's not so unphysical. And if you do all of this, this Hilbert space of 0 charge, well, it constitutes states of finite energy and angular momentum. It contains all hard, high-frequency scattering processes because all of these dressings are contained with really, really low frequency, and all extra charges that I have to add in, I can put behind the moon, I guess. And it's a separable. It admits a countable basis. I can compute amplitudes on the space. Everything is. Consequently, there is a well-defined, I really had to mangle the theory to get here, but there is a well-defined unitary S-matrix in massive QED, if you do all of these things. Okay? And so what I'm going to show you is that even this completely fails in all other theories in the last 5 minutes or so. Any questions? Okay. So let's just do massless QED. So now I'm just going to let the electrons come in from Scry as well. And in massless QED, we don't have a contribution from any charges at time like infinity, but we have that contribution due to the massless charge currents coming in from Scry. And the analogous construction is to pair eigenstates now of this incoming charge current flux with the memory. However, when you do this calculation, which is not a difficult calculation to do, what you find is the eigenvalue of this charge current is a delta function at the position at the place at Scry that this charge current comes in. So let me back up. I'm now sending in massless charge currents also with the photons, and these massless charge currents, they come in, in each momentum mode, they come in at a particular, and you end up with the eigenvalue ends up being a delta function on the sphere. Okay. So what ends up happening when I end up trying to solve, back up a little bit, when I end up trying to solve this exact equation, but now this is replaced by a delta function, that means that I'm introducing singularities in the memory. This charge was before in the massive case was a smooth function of angles because it's just the linearized solution of a massive charge. Replacing this charge with a delta function of angles, and I'm solving for this equation, which means that the memory is now going to have these singularities. Okay, so I'm now sending in, as opposed to just naive, sending in some soft radiation, it's going to have really bad angular behavior, and this bad angular, and I'm going the wrong direction in this, let's go this way. This bad angular behavior has already been known. These required dressings have these so-called collinear divergences. The collinear divergences is basically when the photon, the angular, it's exactly this. Basically, the photon is required to have high, fluxes right where the electron is also coming. Okay. like large fluxes right where the electron is coming in, infinite energy. Basically, the memory is so badly behaved that the electric field cannot be squared. That's basically the point. These collinear divergences have been known for a long time, since the 60s, but the solution to them was to basically smear out or remove at very low, at high angular this terrible angular behavior. You can remove it by putting a high L cutoff in your basically put a cutoff at small angles basically in your function. If you put a small cutoff in angles at some high L, you can get a state of perfectly well-defined energy and angular momentum and everything. However, none of them can be Faddeev-Kulish states. The eigenstates of the charge are required to have these collinear divergences. So states with finite energy exist, they just don't. Faddeev-Kulish would tell you to throw them out. So if you do the Faddeev-Kulish construction, all states are unphysical. They have infinite energy, except for the vacuum. Okay, in GR, we can do linearized quantum gravity first. And just to make it interesting, let's throw in some massless, energy from infinity. So as opposed to some stress energy from infinity, so what was there before was the total, it was the energy due to gravitational waves, but now I'm just going to throw in some any massless fields that I want instead. And in linearized quantum gravity, you can again, repeat the Faddeev-Kulish construction. Turns out there are no collinear divergences in the same way. The memory and the radiation is not so badly singular and is well defined. However, there's a more elementary problem. You can't set this charge to 0. Another way of saying that is I can't hide mass behind the moon. If I set this charge to 0, that would momentum to 0 of the incoming state, and there aren't a lot of states with no form momentum. It's just the vacuum. So all of the Faddeev-Kulish states in linearized quantum gravity have undefined angular momentum now, because I can't set this charge to 0 except the vacuum. Okay, so this is already a bad spot, but let's make it a bit worse. So in full quantum gravity, we can do this again. And again, we can't set the charge to 0. That would require the form momentum to vanish. But I've been talking for about 40 minutes now, and you might say, just give me one, just forget angular momentum. Let's just, think of a Faddeev-Kulish Hilbert, non-zero definite charge. Let's just, if you can give me that, we can at least say that the Hilbert space would scatter into itself. It wouldn't have well-defined angular momentum, but maybe you don't care about that. But we prove the following theorem, which is that the only eigenstate for any value of this charge is the vacuum state with 0 eigenvalue, meaning no memory and no energy. So you can't demand, so the only eigenstate for any value of this charge is this vacuum state. And let me just give you the intuition. The memory and the energy in quantum gravity are not independent from each other. And the energy is what's contributing to this formula. So, for example, send in an incoming graviton with no energy. Now let's do the Faddeev-Kulish thing right now. Send in a little bit of memory to pair with that incoming energy and get a definite charge. Right? That's what we did before, but now we're going to do it with this formula. I'm trying to correlate this term with this term. But that any state of incoming memory is going to have, it'll have as small energy as you want, but it can't have 0 energy. It's going to contribute to the second term. And then so that means that now I have to send in a little bit more memory in order to cancel off the extra contribution that I just got. But that little contribution of memory is going to carry some energy. And that's going to contribute to the second term again. And this process we proved by completely independent arguments. That's not this kind of heuristic thing that I'm explaining, will never converge. There is no eigenstate of this thing, except the vacuum where you started with 0 and 0 in both terms. Okay. Okay, so this is a pretty depressing talk, I guess, because I'm explaining why nothing's going to work. So let me just make a more finer point. There is no preferred Hilbert space for scattering in general, not just quantum gravity, but in particular quantum gravity. except for in massive QED, where it's really should be thought of as more of a fluke. And non-Faddeev-Kulish representations, which are these direct integral representations that I mentioned before, we also show also fail. Okay, so what are we supposed to do? Let me just conclude with my last slide. What are you supposed to do? Well, let me just stress a few things. Correlation functions are perfectly well defined. Remember, I gave you states with memory as well as states without memory. So the correlation functions of states of memory were really easy to write down. They just correlation functions in some very nice way. They were perfectly well defined, and all the correlation functions of all states that arise in scattering theory are perfectly well defined. What we're showing is that all the states relevant for scattering theory don't live in one Hilbert space. Okay, they just don't live in there. And there's a really nice way of thinking about quantum field theory that makes it immediately clear how to proceed. And there's a review article, well, there's a nice review article by Hollins and Wald in 2014. There's a much more recent review article aimed for a broader community written by Witten in this year, which really explains this point really nicely. So it's really the question of how you think about a state. So the standard approach to thinking about a state, which is going to be equivalent to how a little bit nicer. So a state in a Hilbert space, well, first can be just always expressed as a list of correlations. So if you give me a state in Hilbert space, I can write it down as just a list of correlations. Okay, can't stop me. Conversely, however, if you give me a list of correlation functions, which satisfy some rules like commutation relations, positivity, and some other rules, I can always construct by a nice simple construction called the GNS construction, a Hilbert space under which those list of correlation functions always live. Okay, so where the list of correlation functions is then packaged as a vector in this Hilbert space. So what am I saying? I'm saying that if you view a state as a list of correlation functions, it's equivalent to viewing it as a vector in a Hilbert space. There's no difference between these two. However, there's one nice extra property, is that if you consider states just as lists of correlation functions and never ask me what Hilbert space they live in, I'm freed in choosing from advance any particular Hilbert space. And I can talk here without ever telling you what Hilbert space I'm in. And I can explain more that every question about quantum field theory is actually a question about correlation functions, and it's nothing to do with the Hilbert space that have come from. So starting with some inset of correlation functions, which is perfectly easy to write down. This is why the paper is so had to develop this approach. If you start with a list of correlation functions with whatever memory, whatever charges, you can dress them, you can decide not to dress them, you get to decide this. One should then be able to calculate, and this is the ongoing work that I mentioned at the beginning of this talk, one should be able to calculate the outset of correlation functions by the same sort of LSZ perturbative methods that one uses in standard S-matrix calculations, but without ever telling you what Hilbert space is. The set of is perfectly well defined without ever explaining it. And therefore, these S-matrix should be well defined in this other framework. And so it would be really interesting to develop this. It would be manifestly IR-finite because I've never told you that all of the states have to have a finite norm with respect to any norm. And it would just be perfectly well defined. So let me end with the summary and then take a lot of questions. So again, IR divergences, states with memory are perfectly well defined at the level of correlation functions. They're only bad in IR divergent if you try to, stick them into a Hilbert space that they don't belong in. In massive QED, you can stick them in, after a lot of mangling, you can stick them into a Hilbert space which is in some sense preferred because you can, it works in some sense, but as opposed to a proof of principle, we really are trying to explain that it should really be viewed as a fluke, that it works. Non-Faddeev-Kulish representations also don't work. I haven't had time to explain that today. However, what I hope I've explained is that a well-defined, manifestly infrared finite scattering theory can be in principle constructed by developing a map between in and out correlation functions between a suitable space of them. And that's what we did in our paper, where we tried to really explain what the rules are for that. Okay, so let me end there and take any more questions.
Yeah, so I guess the difference from the QED case that makes it so difficult is that like your charge is basically mass now, and it's harder to fudge the.
Well, that's one difficulty. Yeah, I mean, that is a large part of it. Is like you're trying to find eigenstates of this charge, but you're well, it's not immediately obvious you're going to fail. Like the fact that the charge is a mass. I mean, even when we realized that linearized quantum gravity is not going to work because if you really wanted Lorentz to act, you have to go to the zero mass sector basically, and that's not going to work. However, there was some hope in the community in general that forget Lorentz, let's just get some space of eigenstates or some of this charge for some other value, and that would scatter into itself at least. So you would at least have some control over dynamics. I mean, even if you can't ask, is the S-matrix Lorentz invariant? You can't ask that question. But I mean, I would want to ask that question. Some people may not want to ask that question. But what we're basically showing is that that's not going to work either. So, yeah. So part of the answer to the question is partially yes, but then also I think in gravity it just significantly works just because the gravitational field just contributes itself. Like you can't independently specify the memory and the energy of the radiation. They're kind of in this very tightly controlled manner. Yeah.
Yes, I have a question. So now, let's say that you have this well-defined scattering theory between these in-correlation functions and out-correlation functions.
Yeah.
So the S-matrix in this context is a map between what and what?
We just said it.
I mean, is that gets the space in correlation?
Yeah,
that's a linear space that.
No, it's not linear in the same. It doesn't have this. It has just the right structure that you can ask all physically relevant questions, but it's not a linear space in the same way. I can. Okay. Yeah, let me just explain this for a second. I mean, so the word algebraic might scare people, but basically the key thing is that you think of omega basically as you have a well-defined algebra of in observables and out observables. You give me every observable that you're interested in for the in states and the out states. Okay. And what is a state? A state in this particular manner is thought of as a map between the algebra to complex numbers. So what is that? Well, that's a formal way of saying basically a state is defined by giving me a list of endpoint correlation functions. Okay. With satisfying some rules. And what the S-matrix is then, well, it's really, the terminology actually comes from a paper by Hawking in the 90s, where he tried to generalize the S-matrix in some way. I mean, it's called the super scattering matrix in this context. That's just the terminology. The key thing is that the S-matrix would then be a map from this, as you were just saying, an in correlator to an out correlator. But there are rules to this game. And in particular, like you could formalize every statement that's standardly stated about, the S-matrix as a unitary map and things like that can be rephrased in this language. So, for example, conservation of probability, that's a very trivial statement because the identity operator lives in this algebra. And so the map between in and out better preserve the fact that, the expectation value of the identity is 1. Pure-to-pure evolution, there's a way of formulating what the fact that this is a pure state fully in terms of the correlation functions and never saying, well, what representation it lives in. And the most non-trivial, but the most important statement is the probability of measuring observables. Usually so a state basically at this level is again this list of correlation functions, but that means that it also gives you the expected value of all powers of every observable, which means that if I tell you the moments of every observable, I've told you uniquely a probability distribution. And so therefore you can then say, the moments of every observable is determined by its correlators, and therefore you can explicitly say what is the probability in a particular state of measuring any value of any observable. And so in this context, this would be the rules of the game. And you can just do everything that you normally would do in scattering theory. The only thing that it doesn't give you is an amplitude. What is an amplitude? An amplitude is an inner product between an in state and an out state. That doesn't exist in this at all in any infrared finite manner. But an amplitude is not the physical thing. This is physical. Like I tell you what the correlators are of some observable, and I tell you the probability of measuring it. So in some sense, the amplitude is a nice tool, but it's not going to be present in any IR-finite theory. Does that answer your question?
Yeah.
Yeah.
So even in non-relativistic Coulomb scattering,
Yes.
With no photon problem, there's still a Coulomb phase.
Yeah.
And the Kulish construction doesn't really take into account the Coulomb phase in quantum field theory.
Yeah. Yeah.
So my question is this a similar phase problem in quantum gravity?
Oh, let me first answer, like I didn't mention the phase even in massive QED. So the phase is basically coming from how you define the observables at time like infinity, as limits of Fock observables. The standard phase, if you're doing this in Lorentz gauge or something like that, you get this logarithmically divergent phase. There's basically a way like that. So that's basically a statement is what do I mean? Another way of rephrasing it in this language is what do I mean by the algebra of the observables at time like infinity? And there's this work by Dollar that shows how to map the a bulk observable to this to here by basically trying to effectively killing this logarithmically divergent phase. That exact phase will appear if you have massive fields in gravity all the way at time like infinity. So that exact kind of phase does appear, and there's I don't know of any particular paper that has pointed that out, but it is true that you will get this, but you deal with it in the same way that you deal with Dollar's prescription.
So that's the practical thing. You actually want to, do some calculation. Does that mean you essentially have to know the memory of the final state exactly to do this calculation?
No, you will get so. You would if you wanted to do things the standard way. You would. Like I would need to know what the distribution of the of the state is in memory in the out state to be able to guess what the out Hilbert space looks like and then scatter and pre-choose the out Hilbert space. In this particular, and what we're advocating, you would never have to. The only thing you pre-choose is the out algebra and the space on the space of all out correlators that live in the out algebra. So it's a kind of it's basically the or another way of saying this is that you get an out state by this map. You can then take its expected value with the memory and find out, or you can take all of its memory correlators and find out how it's distributed in memory. But I do not have to pre-choose in advance the state looks like at all. It's like, basically we're just saying that in standard evolution problems, you don't ever pre-choose what your out state looks like. But somehow in quantum field theory, we do this, right? Instead of I just tell you initial data and I evolve. We're basically saying there's a way of doing this exact construction in standard quantum field theory, in scattering theory that is agnostic to how you scatter out to. It does need to assume what the out algebra looks like, but that's like a very weak assumption. Everyone agrees on what the out algebra looks like. The question is, what do the states look like? So in some sense, it's just, we're basically saying like, if I ask, I guess like Franz Pretorius or something, he simulates with initial data at Princeton. I'm only thinking because his office is next to mine. He scatters, he simulates with initial data and evolves out. He never has to tell you what the solution has to look like at late times. He finds out what the solution is. And that's what we're basically saying here, is that there's a formulation of scattering theory that is exactly in the same spirit.
So I mean, your out state or out set of correlation operators is general up to
Completely general.
certain.
Yeah, and it's actually it's very simple to write them down. Like, it's not difficult to write down the rules for these things, because it's essentially a free theory that you're scattering out to. So you know the rules of what the algebra of the free theory is, and all the correlators that you're allowed on. So it's very, very simple to write it down.
If there are no other questions, I'll do it again. I think there are still slots on the